Chapter 6.1 is going to be about properties of exponents. Exponents have some fancy things that happen when you multiply the bases together, so that's kind of what we're going to take a look at. The first property is product of powers. So what this looks like is a to the n times a to the m equals a to the n times m. Sorry, m plus m. So here what's happening, and I'm going to use real numbers for this most of the time, is if a is the number 3, this a also has to be 3, so does this a. If n is squared and m is to the 4th power, I multiply those bases together, my result should be 3 to the 2 plus 4, or 3 to the 6th power. So this is what you'd see in textbooks, especially like college textbooks, anytime they introduce something new. The same letter means it has to be the same number. So all the A's have to be the same number, all the N's and all the M's have to be the same number, but A, N, and M don't have to be the same. It's not illegal for them to be the same, they just don't have to. But anything that is the same letter has to be the same as every other letter in the problem. So let's actually break this down. So if I do that 3 squared times 3 to the 4th power thing, I'm going to expand this out, and this is going to look really familiar by the end of this lesson. 3 squared is 3 times 3, because that's all exponents mean, is how many times should I multiply this number by itself. 3 to the 4th power, 3 times 3 times 3 times 3. Now, how many times am I multiplying 3 together? 6. 2 plus 4 is 6. So that's why this property says to add the exponents. We total up how many 3's are getting multiplied together. Quotient of powers is similar but the opposite. This time I'm going to subtract the exponents. So I'll use similar numbers to last time. If I do 3 to the 4th power over 3 squared, what does that look like when I expand it out? 3 times 3 times 3 times 3 on the top, 3 times 3 on the bottom. And in this situation, since everything's multiplied together, anything that's on top and on bottom of the fraction that matches can get canceled out. So I can cancel out 3's until I run out of them on one of the sides of the fraction bar. So what this just comes out to is 3 squared. Well, let's take a look at the property. It says to subtract the exponents. What's 4 minus 2? Well, 2, so we should get 3 squared. So that's how you can break down this property. Power of a power is when you have exponents stacked on top of each other. So a to the m power, then to the n power, and there we're supposed to multiply the exponents together. So if I have 2 cubed to the 4th power, this one's going to expand out pretty big, but we should end up with 12 2's. Let's see if that happens. So 2 cubed looks like 2 times 2 times 2, but then we have a 4th power outside of that. So now it's going to be 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2. The 4th power means to multiply whatever the exponent's on by itself 4 times. That just happens to be 2 times 2 times 2 in parentheses. So now if we count them up, we definitely have 12 2's multiplied together. All right. So what should come out of this is 2 to the 12th power, and that matches up with the property. M times n, 3 times 4 should be 12, and that's what we get when we expand the whole thing out just with exponents. Next up, we've got one called power of a product. When you have an exponent outside parentheses, it essentially distributes itself into the parentheses. Let's take a look at that. Hold on, I'm going to use actual numbers. So I'm going to do 2 times 3 in parentheses to the 4th power. Now I'm not going to multiply 2 by 3 like we normally would, because that'd probably be the easiest first step. Instead, what I'm going to do is I'm going to expand it out so we can see what this looks like with numbers. So I would do 2 times 3, 2 times 3, 2 times 3, 2 times 3. Now adding and multiplying can happen in any order. So since these are all multiplied together, I can rearrange what's multiplied by what. 2 times 2 times 2 times 2, because there's 4 2's, times 3 times 3 times 3 times 3. So this becomes 2 to the 4th power. This becomes 3 to the 4th power. And that's what we have up here. Is when I have an exponent on the parentheses, I should give that exponent to each thing inside the parentheses. Now, when you're just working with numbers, you can actually evaluate it, but this works with variables as well. If 2 is an x, the same situation happens, x times 3, then here it would be x times x times x times x times x. It'd still be x to the 4th power. So we can't actually get a number out of that, but we can keep track of how many x's should be multiplied. Power of a quotient is very similar to power of a product. In fact, you can think of them as one and the same. The same thing happens. Everything inside the parentheses gets that m as an exponent. So if I do 2 over 3 to the 4th power, that's going to turn into 2 over 3 times 2 over 3 times 2 over 3 times 2 over 3. Now how do we multiply fractions? Straight across. Well, I've got 4 fractions, so I'm going to multiply all 4 straight across. So I'm going to have 2 times 2 times 2 times 2 on top, and 3 times 3 times 3 times 3 on bottom. So I'll have 2 to the 4th over 3 to the 4th. All of these properties can be pretty simply done if you just remember how exponents are supposed to work. You don't have to show your work this way. That's completely unnecessary. This is just me trying to convince you that the property is true. So general rules of thumb, if there's an exponent outside of parentheses, give it to everything inside the parentheses. If you have exponents that are stacked, multiply the exponents together. Otherwise, if you just have same bases with different exponents multiplied or divided, then you're just totaling them up or subtracting them based on if they're alternating on top and bottom, or if they're together multiplied on top. So there's some general rules of thumb to follow that make all of these properties easier to remember. So next we're going to talk about geometric sequences. We had arithmetic sequences, and that was when we added by the same thing repeatedly and it made a linear line. Now we're going to have a geometric sequence that's going to make an exponential growth, which you might remember from a science class or a previous math class. These have a common ratio rather than a common difference, which means it's a multiplier. It's not something you add by repeatedly, you repeatedly multiply by this. So in a geometric sequence, we're going to repeatedly multiply, and we're going to go from -3 to +3. Try to identify some patterns, and that might help us come up with a couple extra properties. So the easiest one to start with is 2 to the 1st power, because anything to the 1st power is just itself. So if we go up to 2 squared, I think most of us know 2 squared is 4. But then 2 cubed, we don't go up to 6. We multiply by 2 again. So now it's going to be 2 times 2 times 2 is 8. So what's happening as we go up is we're multiplying by 2 repeatedly. Times 2. Times 2. Well, to go backwards, what's the opposite of multiplying by 2? And this is going to give us one of our first properties, is we're going to divide by 2 to go backwards. 2 over 2 is 1, and this is going to be one of our properties. Anything with a 0 exponent evaluates to 1. And then we get into negative exponents. What's 1 divided by 2? Well, that's just going to be the fraction 1/2. What about 1 divided by 2 divided by 2? That's just going to be 1/4. And then 2 to the negative third is going to be 1/8. So now, dividing by 2 repeatedly actually gives us a reciprocal of the positive exponent. So these are always going to be reciprocals. And that's going to be another property. Basically, what comes out of this is 2 to the n is equal to 1 over 2 to the negative n. Or 2 to the negative n is equal to 1 over 2 to the n. So what this means is if you have a negative exponent, you can turn it into a positive exponent by changing which side of the fraction it's on. Okay, remember, anything can be a fraction by sticking a 1 under it. So this is a geometric sequence. We'll also learn that this is called an exponential function. And this geometric sequence gives us a couple of properties. Since going backwards, going into the negatives, is repeatedly dividing by 2, what ends up happening is anything with the same negative exponent is just a fraction 1 over the number we would have found at the positive exponent. So it's a really easy way to remember what happens with negative exponents. Okay, you never need to keep a negative exponent. You can always turn it positive by just swapping it to the other side of the fraction. And that's the only thing that has to move. You don't flip the entire fraction, you just move the thing you want. It's actually really clean and convenient. So let's go look at some examples. I'm going to start by evaluating a couple. 6.7 to the 0 power is really easy if we remember one of our properties. Anything with a 0 exponent evaluates to 1. Next up, we've got negative 2 to the negative 4 power. What we want to do with this is use our negative exponent property. This is the same as 1 over negative 2 to the normal 4th power. So then we do 1 over negative 2 times negative 2 times negative 2 times negative 2. Negative 2 times negative 2 is 4. 4 times negative 2 is negative 8. Negative 8 times negative 2 is positive 16. Final answer for this one is 1 over 16. We will always make this move. We will always choose to switch the side to make the exponent positive. Everything's easier to evaluate with positive exponents. Another very common type of problem we're going to see is simplifying exponential expressions. It'll be a big part of the unit. We'll practice this a lot. There's some strategies here. We don't have any parentheses, so we don't have to use that distribute the exponent strategy. But what I do want to do is make sure all the variables get together. And I want to make sure everything has a positive exponent. So there's a really easy thing we can start with. X to the 0 power is always going to evaluate to 1. If you see an exponent of 0, you can always make this choice. So we move on to 4 times 1 over y to the negative 3. But 4 times 1 is just 4, so I'm just going to write 4. Next, we've got a negative exponent down here. So I'm going to shift this to the top to make it positive. So now I'm going to have 4y cubed over 1. And that's going to be my answer. There's no fractions to simplify because it's just 4 over 1. In fact, I don't even really need the denominator because dividing by 1 doesn't do anything. There's no negative exponents, and all my variables are combined. There's just one y. I wouldn't want to see y's in multiple places, but we only started with 1, so we didn't really have to worry about that for this problem. This is fully simplified. No negative exponents. No negative exponents. No repeat variables. And fraction is simplified. It's really what we're looking for. We'll do a lot more examples together in class. They go pretty quick. But this is really what we're going to focus on before we get into graphing exponential functions. This is really, really necessary for Algebra 2. Plenty of times I hear Algebra 2 teachers talking about how their students still don't understand the properties of exponents or know how to use them very clean. So we're going to practice that to the point that that's not an issue for anyone. Save the frustration in the future.